In this session, we're going to apply much of what we've learned about higher order functions in one coherent example. The task here is to find fixed points of functions, and the application of the task will be to our well-known square root example. So what is a fixed point? A number x is called a fixed point of a function f if f of x equals x. Let's see that in a graphical example. Let's suppose we have the function that maps x to 1 plus x over 2. So the graph of that function would look like this. And that would be the diagonal. And that would be 1. And the fixed point would be where the diagonal hits the graph of the function. That would be 2. Turns out that for some functions we can locate the fixed points by starting with an initial estimate and then applying f repetitively. So we start with x, then we compute f of x, then f of x, and so on. And for these functions, at some point the value will not vary anymore, or the change will be sufficiently small so that we can declare that we have approximated the fixed point. So for functions that satisfy that property, we could write the following fixed point algorithm. I will go into the worksheet and study it directly. So that algorithm is, if you look at it closely, it's a close derivative of what we did for square root. We have essentially an iteration method that tests whether our guess is close enough to the result, and if it's not, then we iterate. And the improved methods that we had in the square root would now be this f method that we pass as a parameter. So let's try this method out for our function that maps x to 1 plus x over 2. So let me write fixed point x to 1 plus x over 2, initial value 1, and we would get something that's very close to 2 as expected. So now that we know how to do fixed points, can we somehow get new insight in our square root function? Previously we gave you Newton's method essentially as a fact. That's the sequence that you have to use for your iterations. Can we somehow derive that sequence? Well, in fact, yes. So here's a specification of the square root function. What is square root of x? Well, it would be a number y such that y squared equals x. That's what it means to be a square root. Now we can do just some simple algebraic manipulation. So we divide both sides of this equation by y. So we get square root of x is the number y such that y equals x divided by y. But what that means is that square root of x is the fixed point of the function y to x over y, because if you put y in and you get x over y, and x over y is the same as y, then that equation is satisfied. So a solution of the equation is the same as a fixed point of this function here. Now with that knowledge, we can try to revisit our implementation of square root, make it simpler by just plugging it into our fixed point finder function. So that would give square root of x double equals fixed point of this function that maps y to x over y and some initial value 1.0. Let's try that out in the worksheet. So we would have def square root of x double equals fixed point of y maps to x over y and 1 as the initial value. And let's try with our square root of 2. And we get, unfortunately, an infinite computation. This doesn't converge. Why not? What happens? Well, to find out more, we can use println as a debugging help. So let me just add a println statement at a good point. So I guess a good point is in the iterate function, where we could say for each iteration step, we want to write what the current guess is. So we write guess equals and then current guess here. So if we do that, then we see that our guess oscillates between 1 and 2 all the time. And if we do the computations for square root, I encourage you to do that, and you will find that yes, indeed, if you trace the execution using the substitution model, then that's precisely what will happen. So how can we do better? One way to control these oscillations that we were seeing is to prevent the estimation from varying too much. And one way to do this is by averaging successive values of the original sequence. So instead of going 1, 2, 1, 2, we take the average of two successive values, and that would give us 1.5, and that would set us on the right path to convergence. So let's try that. So what we want to do is, instead of saying x over y, we want to take the average of the two values. So that would be y plus x over y divided by 2. And we get back to the square root functions that we've seen in the first week. In fact, if we expand the fixed point function fixed point and plug in the definition of this average damping function for square root, then what we will find is that we get back a very similar square root algorithm than the one we've seen last week. So it's no surprise that we get the same results back. So the previous examples have shown that the expressive power of a language is greatly increased if we can pass functions as arguments. I'm going to show you next that it's also very useful to have functions that return other functions. And I'm going to show you that with fixed point as the example. Let's go back to our observation that square root of x is a fixed point of the function that maps y to x over y. We have taken that observation. We've seen that square root doesn't converge that way, but we could make it converge by averaging successive values. This technique of stabilizing by averaging is general enough to merit being abstracted into its own function. Let's see what this function would look like. We would have the function average damp. It takes an arbitrary function from double to double. It takes a value x of type double, and it then performs it computes the average of x and f of x. Let's do an exercise. Given fixed point and average damp, can you write a square root function that uses both functions? So let's see how we would solve this example. I've given you the average damp function that we developed on the slide. What would square root be now? So square root would be the fixed point of the function that maps y to x over y with initial value 1, but that was the one we did that didn't converge. So what we do is we use average damp on that function here. And if we run it, we get the expected square root result. So what average damp is it's a function that takes a function, namely this function that is at the root of the square root specification, and it returns another function, namely the function that is essentially the same iteration, but with average damping applied. So it's a function that takes a function to another function. If you look at this definition of square root, then I think you would agree that it's probably very difficult to write something that is clearer and shorter than this very definition. We came from the specification of what it means to be a square root. We derived that the solving the equation for square roots means taking the fixed point of this function. We determined that we needed to take averages to dampen the oscillation, so we used this average damp function in the middle, and we are done. So in summary, we saw last week that functions are essential abstractions because they allow us to introduce general methods to perform computations as explicit and named arguments in our programming language. And this week we've seen that these abstractions can be combined with higher order functions to create new abstractions. So that's a very powerful way to compose and abstract programs, and as a programmer it's always good to look for opportunities to abstract and reuse. It's not true that the highest level of abstraction is always the best one. Sometimes it's actually better to stay a little bit more concrete, but it's important to know the techniques of abstraction so that you can use them when they're appropriate.